In this lecture, we are going to discuss about calculation of residue at a pole of order m. Residue at a pole of order m. Let z equal to a be a pole of order m of fz at fz, then Lorentz series expansion of fz about z equal to a is fz equal to sum over n ranges from 0 to infinity a n z minus a to the power n. Here z equal to a is a pole of order m. That means principal part will contain m terms, that is z minus b1 by z minus a, b2 by z minus a square up to bm by z minus a to the power m. Then simplify, we will get here, if I simplify this is the highest power, so this will be z minus a to the power n plus m. Here it will be b1 z minus a to the power m minus 1, because this numerator is this denominator is taken to numerator, and it will be m minus 1. Likewise here b2 z minus a m minus 2 goes on up to bm. So write this z minus a to the power m f of z is equal to sum over n ranges from 0 to infinity a n z minus a to the power n plus m plus b1 z minus a to the power m minus 1 plus b2 z minus a to the power m minus 2 plus dot 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 plus bm. Now taking m minus 1 at derivative, we get if I take m minus 1 at derivative in the left hand side, I will get this one. In the right hand side, we are going to check out what we will get here. If I take this first derivative, then this is the first derivative, n plus m minus 1. Then again in the second derivative, this is n plus m minus 1 z minus a to the power n plus m minus 2 goes on. In the n plus m minus 1 at time, it will be this one, so goes on, it is n plus m minus m minus 1. In the first it is 1, in the second it is minus 1, in the m minus 1 it is m minus 2, and here it is z minus a, and here in the first it is minus 1, so this is n plus m minus m minus 1. So this cancel out, here it will be n plus 1 at power. Here it will be n plus 1 at power, n plus 1 at power, and here it is cancel out, this is plus 2, so n plus 2 at power, n plus 2 at power, n plus 2 at power, n plus 2, this is n plus 1 at, so write this here, it will be summation n ranges from 0 to infinity a to the power m, n plus m, n plus m minus 1, n plus m minus 2 goes on up to n plus 2, and here power of z is z minus a n plus 1. Okay, then here in b1, next is this. Here first is m minus 1, z minus a, m minus 2. Okay, here then second m minus 1, m minus 2, then z minus a, m minus 3. Okay, in the first derivative we have this one, 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 m1, m minus 1, m minus 2. In the second it is m minus 1, m minus 2, m minus 3 goes on. In the m minus 1 it is m minus 2 goes on up to m minus 2. So m minus first derivative it is minus 1, then it is m minus 1 it is m minus 1, z minus a it is m minus m. The first it is 1 more than the number of derivative, that's its first derivative. So in m minus 1 it is m and it is m minus 1. So m minus 1, m minus 1 cancel out, this is 1, m minus 1, m minus 2 up to 2, 1, and it is z minus a to the power 0. That means this is 1 and this is my factorial. This is b1 factorial m minus 1. All the remaining derivative is less than, all the remaining derivative will be 0 because m minus 2 is less than m minus 1. So next, taking limit z tends to a, we get in the right hand side in the left hand side it is limit z tends to a, this. In the right hand side if I put z equal to a, this will be 0. Here it is independent of z minus a, so this will be my this one. Limit z tends to a, d of m minus 1 dz m minus 1, then z minus a to the power m f of z, which is equal to b1, that is factorial m minus 1. This implies b1 equal to 1 by m minus 1, and this is limit z tends to a, d of m minus 1 dz m minus 1 z minus a to the power m half of z, this one. This is the residue of the function. We know b1 is the residue of the function fz at pole z equal to a of order m. That is residue of fz at pole z equal to a is given by this one, m minus 1 limit z tends to a, d of m minus 1 dz m minus 1 z minus a to the power m fz. Next, method 2, if z equal to a is pole of fz, pole of fz of order m, then Lorentz series expansion of fz about z equal to a is fz equal to sum over n ranges from 0 to infinity a n z minus a to the power n plus b1 z minus a. Since z equal to a is a pole of order m, I can write this z minus 8 square plus dot 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 plus bm z minus a to the power m. In the next step, I will simplify this as f of z equal to sum over and ranges from 0 to infinity a to the power m z minus a to the power n plus m, then b1 z minus a to the power m minus 1 plus b2 z minus a to the power m minus 2 plus dot 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 plus bm. I have already explained you how to get this one. Then z minus a to the power m. If I consider the numerator equal to phi z, m, where phi z is my sum over n ranges from 0 to infinity a n z minus a to the power n plus m plus b1 z minus a to the power m minus 1 plus b2 z minus a to the power m minus 2 plus dot 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 plus bm. Okay, where phi z is analytic and phi of a is equal to bm and it is not equal to 0. Therefore, fz can be expressed as phi z by z minus a to the power m. This implies now taking m minus 1 as derivative. This can be written as phi z equal to z minus a to the power m f of z. Taking m minus 1 as derivative, we get phi of m minus 1 z is equal to the m minus 1 dz m minus 1 z minus a to the power m f of z. Now we know this is equal to, from the first method, this portion is equal to, this portion is equal to b1 factorial m minus 1. So write that one, and this is taking limit z tends to a, we get in the left hand side it is phi m minus 1 a, here it is b1 factorial m minus 1. This implies b1 is equal to phi m minus 1 a by factorial m minus 1. Thus, if fz can be expressed as this phi z by z minus a to the power m, then residue of fz at z equal to a, pole z equal to a of order m, is given by m minus 1 derivative of phi z at z equal to a by factorial m minus 1. Now we are going to solve some questions. Examples. Find the residue of fz given by z plus 1 by z minus 1 whole square at z equal to 1. Solution. Poles of fz are poles of fz are z minus 1 is square equal to 0. Poles of fz is obtained by equating denominator to 0. This implies z equal to 1 is pole of fz is a pole of order 2 of fz. Now residue at z equal to 1 is residue at pole of pole z equal to 1 of order 2 is given by 1 by 2 minus 1 factorial limit z tends to 1 d by dz 2 minus 1 summation z minus 1 square fz. Is this the formula? Yes, this one is the formula. So next, put the value of the function, that is this one, equal to limit 1 by 1 factorial is 1. This is z1 d by dz z minus 1 whole square. Here this is z plus 1 whole square by z minus 1 whole square. This is this one. So this is equal to limit z tends to 1 d by dz. Here if I expand this function, this is the value. Next differentiate this one. The limit z tends to 1 d of dz is derivative of the function will be 2z plus 2 plus 2. So put z equal to 1, you will get 4. That is residue of fz at z equal to 1, which is a pool of order 2, is this one. Next, take another question. Find the residue of fz when fz is given by this function at z equal to ia. Answer. Poles of fz are obtained by equating denominator to 0. This implies z square plus a square is equal to 0. Z equal to plus minus ia, ai, which are pole of order 2, order 2 of fz. Next, we can express the function fz as this form: z plus ia and z minus ia, which are the factor of z square plus a square. We have seen this. So this is square. Now I can take this phi z is equal to 1 by z plus ia whole square. Then this is z minus ia square, where my phi z is equal to 1 by z plus ia whole square. Now this is of our second method. My function can be expressed in this form. So residue at z equal to a is this one. Here it is pole of order 2. So residue is given by, therefore residue of fz at z equal to ai, pole of order 2 is phi of 2 minus 1 ia by 2 minus 1 factorial. That is residue of fz at z equal to ai is given by pi dex ia divided by 1 factorial. That is 1 factorial. We have phi z is equal to 1 by this phi z is 1 by z plus ia whole square. So phi dex z will be my minus 2 by z plus I a cube. Therefore, value of phi dex at ai will be my minus 2 by 2 by ai plus I a cube. That is minus 2 by 2 I a cube. That is equal to minus 2 by 8 I cube a cube. That is equal to 1 by 4 I. This is plus a cube. Now this can be written as 4 minus a cube, which is the required residue at the pole z equal to ai of order 2. With that, I would like to conclude. Remaining will be in the next lecture.